Hello everyone, this is our process control lab in which previously in the previous video we have seen how to model a first order system using MATLAB simulating tools and to determine the various parameters, process parameters of an unknown system. That means if you are having a real-time process which is having certain parameters like process gain, delay part, that is our dead time, and the time constant, these parameters we have to determine from the process itself. So that part we have done in the previous video I have uploaded. So it was first order system. So now today we will see how to model a second order system into a first order system. That means it is a second order system. We will model the second order system in terms of a SOPDT. That means the process will be in terms of second order. That means the order of the differential equation will be 2 s square. You can see the transfer function is g of s equal to 1.0 e to the power minus 2s. That means this is the delay part divided by 10s plus 1 into 5s plus 1, right? So here this is nothing but 50s square plus 15s plus 1, and here is the delay part which is 2 seconds. Okay, so the procedure will be the same to determine the sustained oscillation or uniform oscillation with constant amplitude. So here is a PID block. We have gradually increased slowly the value of proportional gain, which is Kp, from here, and I found at 8.254. see, whenever you increase gradually the proportional gain, at a point you will see it is at highest possible oscillation. After that it becomes unstable, right? It becomes unstable. So at that point we need to change the value of Kp in decimal points. If it is required, we can also go for the fourth decimal also. So here at 2.5, because we have to increase this Kp value very much slowly at that point, whenever it starts to go towards the unstable system, from steady state to sudden transient state, suddenly at transient state. At that point we need to increase slowly the Kp value. So at this point 8.254, I have found this uniform oscillation. So let's see, the runtime I have given as 200. Let's save. Okay, initially let's disconnect this part, integrator part, and see just the uniform oscillation. This is the sustained oscillation or uniform oscillation. The procedure to determine T1 and T2 from this oscillation will be the same as I have uploaded the previous video. You may go through that video also, right? So whatever T1 and T2 I found, which is 6.347 and 23.096, right? So from T1 and T2 we will calculate the value of Tu, that means ultimate time period, T2 minus T1, which is our ultimate time period, correct? And from this ultimate time period, that is 16.749 seconds, we will determine the value of omega c, 2 pi by Tu, right? And from that we will determine the value of k also, right? So at that point value of k and as well as the value of theta and tau also. So at that point tau will be only having single value, right? So that means it is in first order system. The system will be the same, but I am representing the second order system in terms of first order system, right? And we will see the difference between these two. We will plot the Bode plot as well as the Nyquist plot for these two, and we will compare the output for both, correct? So after connecting these two, we have to calculate the calculate the value of k. Once I have to put the value as 23.096 and run. This input and output value we have to note down, and then again put the value 16.749 seconds, and again we have to note down the values for input and output. This is nothing but the integrator part. It will integrate the response or the graph for 6.34, sorry, it will be 6.347 for 6.347 seconds, and then it will integrate it again. Whenever I will put this value, it will integrate for this time period only. So from these two values we can calculate the value of k, as we have already seen in the last video also. So this is the similar procedure for second order systems also, but whenever I am determining these parameters, it is converted into a FOPDT system, but the system will be same, system characteristics will be same, but it is converted in terms of first order system, right? Now we will see what is the difference, or we will compare. In short, I can say we will compare the response of both the systems. We will plot the Bode plot as well as the Nyquist plot for both the systems, this one as well as the FOPDT system also. So let's see the FOPDT system, whatever we have determined from this second order system. So this is the first order transfer function. The k we have determined from this procedure, which is 1.00066, and tau is 21.84268 seconds. So this is tau, this is k, and the value of theta, which is the delay part, is 4.51147, right? This is the transfer function. So in short, we can say it is 1.00066 into e to the power minus 4.51147 s divided by 21.84268 s plus 1. This is the transfer function. You may also note down from here also the transfer function, as for the second order it is written over here. So we can also note down the transfer function for the FOPDT system, this system in terms of first order, right? So here we will now plot the Nyquist and as well as Bode plot. Here the comparison for the output we can easily observe from here. Let's make it 200 and run the system. After that, this is the output of both the systems, for the first order as well as the second order. A slight change occurs, but it is tracing down the same, right? The delay part is little different for the first order, and the k and tau is slightly different. So this comment or conclusion, this comment can be made from this observation, or from this output, whatever we are observing in this graph. We can say it as a result of this experiment. And as well as one more part is there, which is also an important part for the comparison of these two systems, which is to observe the Bode as well as the Nyquist plot. So let's go for the Bode and the Nyquist plot, right? So for that we need to write some commands in the command window to plot the Nyquist as well as the Bode plot. So let's write the commands. First of all, we need to define the transfer function, which is s equal to tf of s, right? S equal to tf of s, which is a continuous time transfer function. So after that, two systems, which is one is in terms of second order and one is in terms of first order. So let's define these two transfer functions. System 1, let's name it as system 1, is equal to 1 into exponential e to the power, that means exponential within bracket minus 2 into s divided by 50s square plus 15s plus 1, right? 50 into s square, 50 into s square plus 15 into s plus 1, right? This is the system 1. Then after that, system 2 is equal to exponential minus 4.51147 into s into 1.00066, which is the value of k, divided by within bracket 21.84268 into s plus 1, right? This is the system 2. Okay, these two systems are already defined. Now plot Bode, B-O-D-E. Let's write Bode for system 1, right? It will plot the Bode plot. This is the Bode for system 1. We will hold this one, hold. After that, Bode for system 2. Right? Bode for system 1 as well as Bode for system 2. This is the Bode plot for system 1 and 2. Both Bode plots have been plotted. So from here we can see the comparison. So in the resultant conclusion part or comment part, we can easily compare these two systems in terms of Bode plots. and now we will plot the Nyquist plot, right? So figure, write figure comma Nyquist for system 1, which is the Nyquist plot for system 1, and after that hold on, then Nyquist for system 2, right? Both the Nyquist plot have been plotted, and as well as the Bode plots also. These are the Bode as well as the Nyquist plot for the system in terms of FOPDT as well as in terms of SOPDT. So these are the comparison and the comments we can conclude from, or the analysis we can done from these two Nyquist and Bode plot also, as well as from the output of that system also, right? Whatever we have seen previously. So this is the whole idea from this experiment, by which we can determine the process parameters from a real-time practical process itself by giving it as a step input and determining the values of gain, delay part, that means dead time, as well as time constant, and also we can plot the Bode as well as the Nyquist plot for these two systems, right, and compare the both. This is the whole aim of the experiment. So for first order system and as well as for second order system, we have done the modeling part and determining the process parameters, right? Thank you.